Okay, so welcome back. This is our fourth and last video of this lecture that we are discussing Bayesian networks. But we are not finished with the topic of Bayesian networks in this video. We will continue in the next lecture, but with a slightly different view. We will discuss different problems and see how we can model those problems using Bayesian networks. So it will be a little bit more about modeling than this basic understanding of Bayesian networks that we are having in this lecture. So now I'm going to pause a little bit and take a look on some theoretical aspects of the Bayesian network so we can get a little bit more understanding about this type of probabilistic graphical model. So we're going to go through a series of definitions, and those definitions are very important for us to understand the representation power of Bayesian networks. And our first definition is an independence map, or IMAP for short. And the graph is an IMAP for a probability distribution P if this separation implies into independency in the probability distribution. So what I'm saying that a map is a way of seeing a connection between the graph. So I draw here a graph and the probability distribution P. And if this graph is an IMAP for this probability distribution, it means that every separation that we can find in the graph implies into independency in the probability distribution. And we saw in our lecture about propositional logic that this implication can be understood graphically as a subset. So if this represents the set of all independence that we have in the distribution P, we can look at the separations that we can find in the graph G, and this separation that we can find in the graph G, and the separation will be a subset of all independence that we have. So if it is the case, this separation will imply into independency, and it means also that G is an IMAP for P. So we can see that we have these two subsets, and we can look at one separation that we can find here, and this is also a part of the independences of P. So that's good, but we can also have something that's here, and we saw this in the previous video. It is the case that two variables are not separated, but they can be independent because the independency is hidden into the probability tables. So that is okay, but in some sense it's a little bit limited because we are not bounding the size of this separation set here, so it can be smaller and smaller. So it means that if we start adding some edges here to our graph, like this edge here, we're going to make this separation set slightly smaller, right? Because we have less separations as we add more connections. So we can keep doing this and keep doing this and doing this as far as we do not introduce any cycles. We are fine with that, and we can get into a DAG that is completely connected. And in this case, we are reducing our separation, reducing. So this is for G. The next one is for this sep for a G prime, and the next one for a G2 prime, and so on. We can limit that, and if we get into a fully connected graph, what we're going to have is a separation that is actually an empty set. So we limit that until we have a fully connected graph that will not assume any independencies. If you look at this fully connected graph, right, it will be an IMAP for P, because we are only saying that the D separation implies independency, and if we have no D separation at all, then we have an empty set. But this empty set is still a subset of the independencies in P. So basically what we're saying is that this idea of IMAP is interesting, but there are many graphs. There are IMAPs for a given probability distribution P, and some of these graphs are very complex. But we know that complex graphs are also inefficient. So we would like to have a graph that is as sparse as it can be. So just saying that a graph is an IMAP for a distribution is not enough. We would like to have something else that would tell us that, okay, this graph is an IMAP, so it can be used to represent this probability distribution, but this is the sparsest that we can get. And this idea comes with the minimal IMAP. And it says here in this definition that an IMAP is minimal if the graph ceases to be an IMAP if we delete any edges from G. So let's draw it again and see if we can get a better understanding of this. So I have my DAG here, right? And we have the probability distribution, and if this graph is an IMAP for P, what I'm saying is that, okay, these separations that we have here is a subset of the independencies that we have in P. But we are saying that if we remove any one of these edges that we have, it will cease to be an IMAP. So basically I'm saying that if we try to remove this edge here, we are removing one edge, and we are adding one independency assumption to this graph. And if we do that, it's like growing an arm here. In some way, you're going to touch the space outside the set of independencies of P. And if we try to remove this guy here, we're going to grow another arm here and assume a non-independency that is not in P. And the same for here and the same for here. So we cannot remove any edges, because in some sense this IMAP is already minimal, right? So we cannot have more independence. Any other independence that we assume for this graph will lead to some invalid independency in the probability distribution. And another concept is called DMAPs, and it stands for dependency map. And the dependency map means that if we have a dependency in the probability distribution, it will imply a D separation. And we know that is not true, right? So if we take a probability distribution that is induced by a Bayesian network, G, then not necessarily G is a DMAP for P, because we know that we may have some independence hidden in the probability distributions. But we also know that we can make G a DMAP for P. So here is actually DMAP. There is a typo in if we choose the parameterization carefully. So we are saying that, okay, we can have the influence, the implications in the two ways, right? So we can have D separation implying into independency, and independency implying to D separation. The first case is for the IMAPs, and the second case for the DMAPs. And if a graph is both an IMAP and a DMAP for a probability distribution, so we call this a perfect map. So perfect maps is exactly what we wanted to have, but we cannot have it in most of the cases. So it will be the case where if you look at the set of independencies for P, and we look at the set of these separations for the graph, they match. So this separation for the graph G, they match. So they are exactly the same. When we have it, is the perfect world, because when we say, okay, these two nodes are d-separated, it will imply that they are independent. At the same time, if two variables are independent, they will be d-separated in the graph too. So this is the perfect world. So we like to have perfect maps whenever it's possible, but we need to understand that for some independence assumptions, we cannot represent all those independent assumptions into a Bayesian network. So one example is these independence assumptions. If you want to represent those independence assumptions, all of them and no more independence assumptions, into a graph, we see that we cannot do that using a DAG. So we can try to do that by looking at different ways of building the DAG. So something we can have like x1 and can have x2. So we needed that x1 and is independent of x2 given y1 and y2. So we have y1 here and y2. And one way of drawing this is, making I1 in the middle here of I1 and y2 being in the middle of x1 and x2. So when we observe these two guys here, we block the influence because we have the sequential triplets here, and they will be independent. So x1 will be independent of x2 given y1 and y2. But at the same time, because here we have this convergent triplet here, it means that if we observe x2, we're going to make y1 and y2 not d-separated. So we break this independence assumption here. And of course, we can try to change this graph and doing something different. So we can change the direction of the edges. So we can do something like this, and okay, we're gonna change and make it like this. But now we have this convergent triplet here in y2, and if we observe y2, we're gonna make x1 and x2 dependent of each other. So you're gonna break this guy here, right? So every attempt that we do, every different graph that we try, we see that we will break one of those independence assumptions, or we will assume another independence assumption that is not in this list. So if you try to represent, to have a graph that represents exactly these four independence assumptions, we cannot do that using a Bayesian network. So it seems that Bayesian networks are limited, so they cannot represent any set of independence assumptions. And that is true. We also see that this exact set of four independence assumptions can be represented in an undirected graph when we study the Markov networks in a future lecture. So by now, it's clear that what we wanted, that are perfect maps, that there is a perfect matching between this separation and independencies, is not always possible. It will happen if we have no independence assumptions hidden in the probability tables, but it should be also clear that for some set of independence assumptions, there will be no graphs that can represent them, so there is no perfect maps for those sets of independence assumptions. So if the dependency maps, they not always exist, they will depend on the dependency assumptions that we have in the probability distribution. Maybe the best that we can stick with are the minimal IMAPs, because the minimal IMAPs, they always exist, and in some sense they are optimal because we cannot remove any edges. If we do that, we assume some independency that's not true in the probability distribution. So in some way, they will lead us to sparse graphs that have as few parameters as possible, and will lead to these compact networks. So it would be interesting to have a procedure to build a minimal IMAP. And there is such a procedure, so this is the algorithm for doing that. It will require an ordering for the nodes. So you take the variables that are in the probability distribution, x1, x2, x3 until xn. So we assume that we have n variables, and we'll take that in a specific order. We can choose the order, and we see that different orders, unfortunately, will lead to different graphs too. The second step is start with an empty DAG and consider a variable xi in the order. And the third step, for each variable xi, so there is a typo here, we identify a minimal subset p. This should be in boldface to be different from the probability distribution p of variables x1 until xi minus 1. So we'll consider all the variables that were before xi in the ordering, such that xi is independent of those variables, not in taking account the variables in p given p, and make p the parents of xi in G. So let's look at one example. I think that's going to be easier for us to understand than reading the algorithm. So I will take this this graph here. So we have this well-known problem of the earthquake, burglary, and alarm, and I will take this ordering here and see what we get as the minimal IMAP. So let's suppose that this graph here is a P-map, is a perfect map for some distribution P. What I mean by that is that if we look here and we find this separation between nodes, we will know that there is independence in the distribution P, and if we don't find this separation here, it means there is a dependence between the variables in the distribution P. So it will be a sort of a representation of all independence that we have for the distribution P. It will make us our life easier as the algorithm asks for dependencies and independencies between the variables, so we can check those independencies and dependencies here in the graph, right? So so let's assume that this graph here is a perfect map for the distribution P, so we can use the graph as a tool to check for dependencies and independencies. Okay, so the algorithm asks for an ordering for the variables, and we have the ordering here. So there is, okay, one mistake here. There is no variable t. So we have a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 variables. Okay, that's correct now. And we started with the first variable in our sequence, that's a. The algorithm asks us to check if we should connect a with the parents, but there are no possible parents here because a is the first in the sequence. So let's move on to the second one, that's b. So a and b are here in our perfect map, and there is no way that we can make one independent of the other because they are directly connected. So yeah, they never will be separated. So we understand that they are dependent. So we have an edge come from A to B. The next step is to move on to the next algorithm, the next variable, and the next variable is C. So C is here on the bottom, and the C must be connected to A because they are directly connected by an edge. But if we have A, right, it will be our minimal set of variables to disconnect C to B. So we do not need to have an edge from B to C because A will block the influence from B to C. So C will be independent of B given A. So that's good. let's move on to the next variable, and the next one is E. Okay, that's the next variable. E is here, right? So if we look at the other variables, there is A, and there is no way to make them independent of each other. So let's connect with an edge. And but now I have that I have here A, and conditional to, we have E and conditional to A. And if you look at C, okay, we can make E independent of C given A by observing here. So there is no connection between E and C, but as I have A observed, there will be influence between E and B, and it means that we need an edge between E and B. Okay, let's move on to the next variable, that is R. And R, okay, cannot be independent of E because they are directly connected, but once I have observed E, it will block the influence of the other variables in our perfect map, so I don't need to connect R to anything else but E. So if we have the same plot that we have here, the same graph, we have E and B, we have A in the middle here being connected, and we have R here, and we have C here, right? So this is the original one, and but if you look at the IMAP, let me remove those edges and see how we did with the IMAP. So with the IMAP, A is connected to B, so there will be a connection like this. A is also connected to C, there will be something like this, and A is connected to E, it's a connection like this, and B is connected to E, there is a connection like this, okay, and C is not connected to anything, and E is connected to R, so we have a connection like this. So this is the IMAP that we found using this ordering. If we change the ordering, we will get different minimal IMAPs. So there is one ordering that will give us exactly this causal causal graph, and but other orderings will give us can give us different minimal IMAPs. So that is one of the problems of this algorithm, that it is sensitive to the order of the sequence of the variables. So just to show you in a little bit more organized way, this is what we get with the IMAP procedure. You should call it the minimal IMAP procedure, and this is the causal one. So if we look at and compare, at least for me, the causal one is simpler to understand, and also it has less edges. So we have one additional edge that we didn't have here, right? So we can use this procedure in order to build those minimal IMAPs, but doesn't mean that it will be easy to understand then. So this is a sort of a summary of what we haven't discussed before. So first thing is that the resulting graph G prime, so here is the G prime, it's guaranteed to be minimal in terms of independencies. So this separation in G prime, so I found here this separation will lead to a deseparation here too in our causal graph, and also an independence in the probability distribution P. this is to hold if we delete an edge in G prime. So any edge that we delete, including this one, will make some additional independence assumption that do not hold in P and will not lead to a deseparation here in the top graph G. So G prime is incompatible with the causal relationships. So yeah, we discussed that. It doesn't sound as clear to me as the G graph, yet it is sound from an independence viewpoint, in the sense that every deseparation that we find in G prime will be present in G too, and also will lead to independence in the distribution P. And it means that the person that agrees with G cannot disagree with the independence in G prime. That's good. Okay, this minimal IMAP is not unique, so we discussed that. It depends on the variable ordering. So if we change the ordering, we get another minimal IMAP that may have less or more edges than we have in this G prime. In a particular way, there is one ordering that will result into G, the causal graph that we built in the beginning. We may have multiple IMAPs for a single ordering. That's true too, since we may find multiple minimal sets P for the same variable xi. So depends on how we run the algorithm, we may choose different sets, these minimal sets P, that make xi independent from the previous variables. So we may have more than one decision, and we may find different IMAPs depending on how we choose the variables that will compose P. So one last concept that we should take a look at is called Markov blankets and Markov boundaries. So let's use this figure here to explain. So suppose that we have this variable A here, and we want to make A independent of all the other variables that we have in the graph. So you would like to know which variables we have to observe in order to make A independent of the whole graph. So in order to do that, we will need to observe the parents of A, because this will block the influence that comes from the top of the graph. We need to observe the children of A, because that will block the influence that comes from the bottom part of the graph. But we also have to observe what we call the exposes of A. In this case, there are two here. These are the variables that have common child with A. So this is one expose, this is another expose. And we need to observe those variables too, because if we have observed the children, this is a convergent triplet. This is a convergent triplet too. It means that this variable here will be able to influence A. So we need to include also the exposes. So we have included all those variables, the parents, expose, and children. So we have isolated A from the other variables in the graph. So no other variables will be able to change our beliefs in A, will change our probability in A. So we call those variables the Markov blanket of A. And if this set of variables is minimal, we call it the Markov boundary of A. So this is the idea. The Markov blanket and boundaries are the set of variables that will make A independent from all the other variables in the graph. And if the blanket is minimal, so we cannot remove any other variables that is there, then we call it a boundary. All right, so we get to the end of this lecture, and so we saw our first graphical model, that are the Bayesian networks. It's implemented with a DAG, so it's a direct acyclic graph. We saw that the graph represents the dependency that we have between the variables, and the parameterization will give us the strength between the dependencies. So we'll compose the second part of the representation. We look at the d-separation algorithm. That is a very convenient and efficient way to detect independencies, and we saw that it is sound. So every d-separation will lead to an independency, but it's not complete in the sense that we can have more independencies that are encoded into the parameterization of the Bayesian network. We also discussed the concepts of I-maps, D-maps, and P-maps. So I-maps are what we call the independency maps, D-maps the dependency maps, and when we have something that is an I-map and a D-map at the same time, we have what we call the perfect map. You would like to have perfect maps all the time, but it's not always possible. What we can have are minimal I-maps, and we discuss an algorithm to find a minimal I-map for a distribution P. Alright, so this is a summary of what we haven't seen so far. I invite you to read chapter 4 from the textbook, and if you want to know a little bit more about this. See you in the next lecture. Then I'm going to start discussing modeling Bayesian networks.